Now I'm pleased to introduce our presenter for today's training, Stephen Eubanks, PE, PMP, and CFM. Stephen is the owner of Stephen Eubanks Engineering, LLC, since retiring after 19 years with the city of Fort Worth. He held several positions in the city's stormwater program, including Chief Stormwater Engineer. His responsibilities included new development review, capital project management, flooding and drainage complaint investigations, public-private partnerships, infrastructure criticality assessment, engineering assistance for maintenance projects. He assisted in the development of Fort Worth stormwater utility and the 2006 Fort Worth Stormwater Management Design Manual, and more recently oversaw development of the city's stormwater master plan. He has spoken at numerous conferences and has developed several workshops and training programs. He was honored by TSPE Fort Worth Chapter as Engineer of the Year in 2016. And now, Stephen, we'd invite you to make your presentation on the challenge of urban flooding.
Okay, can everybody hear me okay? Oh, well, yep. I assume so. So Michael step in if I'm not coming through. First of all, I want to thank three of my colleagues, Burton Johnson, Brenda Gasparich, and Jeff Wanger. When I worked for the city, they worked with me. We derived this from several presentations. We developed it into a 4-hour workshop that we presented at the Texas Floodplain Management Association conference on a couple of occasions, and the Association of State Floodplain Managers National Conference. I've kind of condensed this into about a 45, 50-minute presentation, and let's hope I don't chase too many rabbits and we'll get through it okay. First of all, in terms of context, I wanted to talk to you a little bit about the National Flood Insurance Program. It was created by the National Flood Insurance Act of 1968, and it's really important to know, most people don't discover until after it's happened that homeowners insurance does not cover flooding. It never has, and so flood insurance is basically something extra that you have to buy. The community participation in the National Flood Insurance Program is voluntary based on adopting an approved floodplain ordinance, and flood insurance is required for federally backed loans such as FHA and VA loans only if the community participates. And then the NFIP has produced flood insurance rate maps, but it includes it maps only floodplains along major streams and rivers and in coastal storm surge areas. And we'll get back to that in a minute. Although the NFIP has disaster recovery policies, it depends upon local enforcement at some of the challenges it has. Insurance is voluntary unless federal funds or loans are involved. And what it really does, because it's a federal program, it does make flooding an affordable risk. And before Harvey, it was over $17 billion in the red, primarily due to Katrina and Sandy, but it was never self-sustaining. And I don't have figures on how bad it is now since Harvey came, but I imagine it's probably closer to about 30 billion in the red. But the point is, it's never been self-sustaining. Other challenges is that it uses flood insurance rate maps. And because they're insurance rate maps, they're really not regulatory or planning maps. And so they will represent what a risk is today, even though say future development may increase the flooding a foot or two. Only a community can adopt certain regulations for that, but the flood insurance rate map only shows what the flooding is now based on the best available studies. It identifies only what's called the 1% or the 0.2% risk, known as 100-year or 500-year floodplains, no matter how deep in the floodplain you are. And unfortunately, that's often used by realtors and home buyers to give them a false sense of security that if they're in the 100-year floodplain, they shouldn't expect to flood more than once in 100 years. But that information, is prone to real easy misinterpretation by the unsuspecting buyer. But another real problem is that local tributaries or undersized storm sewer systems are not included in mapping. So therefore, all land not in a mapped floodplain is called Zone X. So every bit of the flooding that you see here is Zone X flooding. It's all due to undersized storm drain systems, or in some cases, small tributaries that are not mapped. But you can see this flooding is very impactful, both on commercial, industrial, city maintenance facilities, as well as residential neighborhoods. Very significant flooding impacts. So the question now is, what really is the challenge of urban flooding? It typically happens in older parts of town. It includes both frequent chronic flooding and occasional nuisance flooding. It could be that the flooding, happens every year or 2 years, but maybe it only gets in the house every 5 years, or it gets in a commercial building. But it's flooding that happens. Either happens only once in a great while, or it happens a lot more frequently, depending on how undersized the system is. And there's typically no affordable solutions available. And it's because if an affordable solution had been available, it would have been built a long time ago. This flooding happens fast, so it's gone in an hour or less. Until the advent of cell phones and folks having access to a lot of video footage immediately, you rarely got pictures of urban flooding. In fact, a lot of these storms happen late at night, so they were in the dark. And it often only received brief public attention. The damages really can also be intangible. Besides the actual flood damage, homeowners experience all sorts of quality of life issues. They talk about every time it rains, they're fearful of more water coming in their house, so they can't sleep at night. I've heard many of these kinds of stories of these intangible damages occurring from urban flooding. Generally, this kind of flooding is not addressed by the National Flood Insurance Program. We've said that the flood risk is not mapped. It's all considered Zone X, no flooding. And it's considered really just a local problem. There's no established recovery process after flooding, like the NFIP has for when major flooding occurs along streams and rivers. And it's a low grant priority. And I've even had floodplain manager call it not floodplain. So somehow it's not important, or it's not really flooding. I don't really understand that, but because it wasn't mapped by the federal government, apparently it's not very important. So before we go further into looking at urban flooding, I want to go through 4 general considerations. The first is water law. In Texas, the water law is really handled by Texas Water Code 11086, where no person may divert or impound the natural flow of waters in the state in a manner that damages the property of another. And a person whose property is injured by the overflow of water has remedies at law and in equity and may recover damages. So what does that mean? It means lawsuits. And I have, sorry about that. And there have been involved tangentially in 2 or 3 different lawsuits over the years. City was only directly sued twice, and it was really something that was more of a private issue. But the folks doing the mediation really like to, the cities have the money, so they really like to get the cities involved. but there's a lot of policy issues involved with some of these lawsuits. A second consideration is what I'm calling the no adverse impact policy. This is from the Association of State Floodplain Managers as it relates to floodplain management. And it says no adverse impact floodplain management takes place when the actions of one property owner are not allowed to adversely affect the rights of other property owners. And it describes that in terms of increased flood peaks, increased flood stages, higher flood velocities, increased erosion and sedimentation, and other impacts the community considers important. Many communities have adopted a no adverse impact policies for new development. And ultimately, that policy should guide solutions to urban flooding. We can't solve urban flooding by putting in partial improvements and just moving flooding from an area upstream and pushing it downstream someplace. That's just not going to work. Our third general consideration is hydrodynamic modeling. Urban flooding is really too complex for traditional modeling and calculations. Hydrodynamic modeling has become an essential tool for understanding urban flooding. It's able really to track overland flow as well as pipe capacity. And but this fully dynamic flow modeling requires complex software. The dynamic wave modeling looks at both the effects of water rising, peaking, and dropping, not just a steady flow rate, like many of us have with, well, what I started out with is HEC 2, it's Hydrograph now. And then storage and routing are built into the analysis of this dynamic wave modeling. And the momentum and continuity are expressed as nonlinear differential equations. And I don't know about you, but I had never have solved any one of these by hand. But fortunately for us, and as long as these computer programs didn't exist, we really couldn't do much. But we do have a lot of software available. Two of the major products are now under the Innovize umbrella. InfoWorks was developed by Wallingford, and XP Swim was developed by XP Software. They're now under the same umbrella. Mike Flood is produced by DHI. The core now has come out with HECRAS 2D, and it's more and more robust since the time I actually originally presented this. I've never used HECRAS 2D, but I've had seen presentations where folks use it for some fairly detailed investigations. There's also other products out there that can be available. And then finally, our fourth general consideration is understanding risk. Now, risk is often defined as the product of the probability of an event occurring times the consequences of that event. The darker shading is basically a greater impetus to take action. It might have high probability and low consequences, or low probability and high consequences, and there's generally less incentive to take action. But as the probability increases and the consequences increases, the risk gets higher, and so therefore people do more to manage that risk. Generally, with urban flooding, public safety is not a major threat. Occasionally there are deaths. The last time this kind of urban flooding from undersized storm drains caused deaths in Fort Worth, there were 2 deaths in 1986, but none back in the 34 years since. Because of FEMA's policies, Zone X, there's nothing that hinders rebuilding, whereas if it was a mapped floodplain, there's all sorts of restrictions. So folks can go right back. They could sell the property and somebody can come right in and rebuild just like nothing happened and put more property at risk. There's a difference. We had one citizen refer to this as chronic flooding. In some neighborhoods, it happens all the time. Other times, other neighborhoods, it only happens once every 5 to 10 years. And so therefore, maybe where it's more periodic, it can be just as devastating when the big floods come. But folks really don't recognize it as an ongoing problem and are really surprised when it happens. But folks manage flooding like they do all the other risks in their life. You know, you can avoid it by moving out of the area that floods. You can cope with it with minor prevention and repair. You can obtain insurance to limit your economic losses. Actually, FEMA insurance, if you're in Zone X, FEMA insurance is fairly cheap. And again, this makes flooding an affordable risk, but it also encourages more flooding and puts the NFIP in greater and greater economic disadvantage. Or you can endure flooding. You just accept it as it comes. You don't store things under your bed. You don't keep things that are valuable low in your house. The water comes in, the water goes out. You don't worry about carpet. I've seen folks that just had a slab floor, and when the water starts coming in the front door, they open up the back door so the water can go through faster and limit the flooding in the house. I kid you not. So let's see what really is the problem of urban flooding. This is South Fort Worth. This is where near where I live. It's a typical neighborhood in Fort Worth. You can see a few little streams. In fact, when I first started going to work for the city, I thought, well, you know, we don't really have much of a flooding issue because there's, you know, not that many streams in some of these areas. And you start looking at what's mapped. You see some of the FEMA floodplain is in purple. The dotted purple is the 500-year floodplain. Everything else is the 100-year floodplain. And you see that some of the floodplain is mapped, some of it's not. But then you put on the storm sewer system and you realize that there's a whole lot of drainage that's really not accounted for. And you do some hydrodynamic modeling, and this is the kind of flooding that you can get in a neighborhood. And you see it can be quite extensive and quite a bit broader than anything that's mapped as a FEMA floodplain. So what are the main causes of urban flooding? The pre-1960 had lower design standards, meant storm drains often were severely undersized compared to current standards. And in fact, in some cities, it's about 1990 when they adopted either the 100-year design, if they have one that's that high. The street grid often ignored drainage patterns, leading to mid-block sumps, and houses and buildings were constructed over the storm drains in some cases. For example, this is one older neighborhood in Fort Worth. We're going to come back to that. It's called Arlington Heights. I pieced together the storm drain maps. You can see a stream going across, but I've highlighted now the path of the storm drain. The plans weren't very easy to read. So there's the path of the storm drain. Now we lay over the neighborhood today, and you see it just kind of goes cattywampus right across the middle of the neighborhood. And we start looking at the flooding, and you see all the extensive amounts that can be flooded. Now, it doesn't look like the flooding is too deep between the next house, between houses, but actually on the next slide, we'll take a little video of this. Let me warn you now, I've got the audio on, and you might want to turn down your volume for just a moment before it gets too loud here in this next video.
That's right there in the street, then the water's every bit of 10 foot deep. I'm almost out of tape. Look at that, man. The dog says, okay, I'm making a run for it. Dog, don't go in that water. Now you're gonna do it in the water circle. He ain't going in that water. He's like, damn, look at what's making my house. Jones, some 2x4s for you. Let's go get them. Go get them, bro. Get him, pup, get him. There's a side. Get this that girls that. Go, dog. Get back up here. Come on. Get back up here. You got what, one storm drain down here? Yep. One. Well, one on this side, one on that side. And they're right there. I mean, it's right there in front of my driveway. But as you see, all the water drains were popping up over there.
Look,
so.
I mean, this is not even slowing down, dude. It's still just powering out of there.
Let's see, all that stuff on Camp Bowie will drain over here.
Yeah.
Okay, I'm back. So, how do we solve this kind of flooding problem? Well, this is every engineer's dream of the best way to solve urban flooding. Unfortunately, not too many of us can come up with the right miracle. So let's look at a few realistic solutions. New pipe on an existing alignment. In this case, to put 2 6x6 boxes in, the buyouts would have to include at least 3 houses and several garages, and the practicality of actually running the line down the alleys is because there's already sewer, electric, and gas in the alleys, would probably actually require a different kind of alignment, but again, that's one of the issues that have to deal with. Another area of town, we did a solution. It showed one little orange line says 3 6x10 box culverts, but when you actually look at where the box culverts would have to be, the only room for them is actually where the houses are. And in that case, you may as well turn it back into a creek. We'll look at an example of that coming up. What about following the street grid to reduce home buyouts? This is back in the Arlington Heights neighborhood. Laid out a little alignment to follow the street grid. And you see at the intersection there, the pipe would be 32 feet deep. Now I sketched this up to show what 32 foot deep would look like. Folks have told me that's an unrealistic diagram, that the trench would actually be narrower and we would actually be able to save the curbs. But nevertheless, you see that even if the curbs were saved, that is really an impractical construction solution with all the other utilities that would be affected, as well as folks having access to their houses. Well, what about tunneling? Tunneling's a really, really neat idea. It preserves the neighborhood. You can go in deep underground, but in this particular case, this was $30 million, but this was about 10 years ago. Probably, if you did a realistic, detailed pricing today, you had really good information, you could still probably do this for maybe about $50 million. But again, very, very expensive to do. We looked at one in the neighborhood of South Fort Worth, over by TCU, where we have extensive flooding. It would be, this particular tunnel would be closer to $100 million in cost, but it would at least allow discharge directly to the river. And we'll talk about why we would go directly to the river in a little bit. In fact, that would be a real good time to do that now, and that's called the hydrologic considerations with conveyance. And I'm going to talk about a little bit from our college days. Some of us remember the unit hydrograph method. The unit hydrograph shows how the storm, the flow rises after a storm. The gray represents the rainfall. The lag time is the time from the rainfall to occur to flow down to the cause the peak discharge, and then the water level goes back down. Now, urbanization, the total volume is greater due to less infiltration. The time to peak is shorter due to faster flow on paving and in pipes. And the peak flow rate may be doubled or tripled from what it was before development. I'm going to give this example. This was prepared by HDR for one of our studies. They were actually looking at a floodplain along a creek, but they had this huge 3 fairly large drainage systems all coming out and the creek starts here in this 6B area. They look about how would you estimate flow coming out of these storm drain areas. The first thing they looked at was the storm drain flow path. These three areas together was about 18,000 feet storm drain path. That would be about 6,000 feet average. And they said that it would more or less, the average flow distance would be 4 feet per second over the total distance, including the collection time, overland flow time. If we had no storm drain, the flow path would be total about 17,000 feet, and it averages only about 1.5 feet a second. So significantly slower flow if there was no storm drain system. So we're going to look particularly at the one in the middle here, the larger one, 342 acres. If it was only overland flow, the time of concentration is 68 minutes, and the peak flow would be 1,100 cubic feet per second. If all the water could fit in the storm drain, it would be a 28-minute time of concentration, and the peak flow would be 1,800 cubic feet per second, which is a fairly significant difference between the two. Now, what I really found interesting in this, and I'm really applying it a little bit differently from what we were looking at, but it here's a hydrograph showing the potential hydrographs for this area. But in reality, the 5-year storm fits in the storm drain pipe, and the 100-year storm doesn't fit in the pipe, and therefore it travels over land. So we've got this now, we've got half the water now traveling through the pipe. That would be the short dotted line. That's the inflow from the pipe. The inflow from the overland, the street flow, has a much longer lag, and it appears actually after the peak is over with. And so the yellow hydrograph shows what it looks like when you put the 5-year storm in the pipe and the rest of it travels over land. So let's look at our 3 hydrographs together, and you find out that really the actual situation is not too different of a hydrograph than if it's all overland flow. The yellow and blue are fairly similar, and they're both significantly lower if all the water were to go in the pipe. So the conclusion for this is that if we're actually going to put a pipe in that neighborhood, we could expect the peak flow to increase by over 60%, from 1,100 CFS to 1,800 CFS if we were to do that. Now, we're going to come back to look at the effects of this in a moment here, but I wanted to talk about another hydrologic consideration, and that's valley storage. This is a measure of a stream's ability to store water as it moves downstream. A good example of this is the Trinity River floodplain. This is across East Fort Worth and North Arlington. And you see the floodplain gets really, really broad, but there is a lot of water that gets stored here. The more that we put in levees and reduce the amount of spread of the water, the less valley storage there is, and so the more water moves downstream. Dallas has areas significantly subject to flooding, but if this valley storage were being removed, all of the Dallas levees would be more frequently overtopped. So let's go back to the neighborhood we were looking at. And we do have valley storage in neighborhoods when the storm drain is undersized. Somebody called that one time living room detention. And it's kind of tongue-in-cheek, but unfortunately you do have detention in the neighborhood or valley storage. Unfortunately, it's in the living room of people. And so it's a catch-22. So looking at now back at our situation, this is downstream of 2 of our areas that we were looking at, and the we're only looking at the north side of the channel. The channel itself is in dark blue. But if the floodplain as it is now, with half the flow in the 5-year flow in the pipe and everything else coming over land, we didn't really do a detailed hydrodynamic model, but this is a fairly decent approximation. And the 100-year flow is what's shown in yellow. And so there's a few houses affected, but for the most part, the water's contained in the street. If we were to put in a 100-year conveyance, just in this section alone, the number of houses affected would be tripled. We could probably expect that, or maybe more than that, on the south side of the street. So what does this tell us? It tells us we've got to remember the state water laws and the no adverse impacts policy, and it makes it very difficult for us to put in upstream conveyance where we're going to cause increased downstream flooding. So in conclusion, our upland flooding is caused by undersized storm drains. Upland flooding caused by the undersized storm drains will reduce the flooding downstream. So living room detention, which is bad for the people upstream, is actually valley storage, which is good for the people downstream. And so the larger pipes we put in, we're likely just to move the flooding downstream. But we need to find a better way to provide valley storage rather than in people's living rooms. And of course, that brings about the magic word called detention. So going back to unit hydrograph, the whole point of detention is to try and control the peak flow, limit it to what it was before urbanization. There'll still be a greater volume. There'll still be a greater length of time at that peak. Some folks have talked about increased erosion issues and things like that. Those are things you have to deal with on an individual basis. But ultimately, it tries to bring down that peak to what it was before urbanization. Now, why would we do detention? Well, flood hazards are, often due to these undersized drainage systems, and pipe and channel improvements can be very, very expensive. The conveyance improvements can push the flooding downstream. We've just looked at that. Here's some examples of the kinds of impacts you might have. And there's the legal implications we've just talked about for causing downstream impacts. So why would we do detention? Well, detention decreases flooding impacts continuously. Everywhere you put in detention, everywhere downstream, from the point you put it in all the way downstream, the flooding impacts are decreased. And detention is much cheaper to build except for land cost. Now, every once in a while, there's a way to get around land cost, but that generally means your detention is doing something it wasn't really intended to do. To my friends at Texas Tech, thank you for the good example for detention. Now, in 2002, shortly after I went to work for the city, I didn't know near as much as I know now about detention, about valley storage. And so we had this same Arlington Heights neighborhood, and we had this little vacant tract of land up at one corner. And I had somebody do a study and say, well, can we put detention there? And how's that going to help us? So his study showed that 108 acre feet of detention were required. 108 acre feet will fill up the bowl of TCU's Amon Carter Stadium. Now, this is the old configuration of the stadium, but the bowl is still the same. And it would fill it up, unfortunately, not once, but twice. And that's a lot of water. Since we're using the example of flooding a football field, I think this was a good example. Now, I had these slides done before before the Texas Tech Jones Stadium flooding pictures came out, but nevertheless, it shows us how much water can be involved. Now, that 108 acre feet translates to 35 million gallons. And when you look at detention in a neighborhood like that, you really find that you can affect up to 76 homes, which is a significant amount of land, a significant amount of buyout to provide detention the level of detention that's needed. In larger pipe sheds, you're likely to require several ponds, and this is the one over near TCU where you'd be having maybe over 150 homes that would be affected, need to be bought out. We did look at what if you did deep detention, if you could get the water to one location and do deep detention and then pump out the water after the storm. It looked like a pretty neat idea. If you remember how storms come in Texas, when we get these, the flooding we have up here in Fort Worth, it's not like the coastal flooding, but most of the rest of the state has the same kind of flooding we do. The thunderstorms that come in the afternoon, and they can stop somewhere and just generate a huge downpour, local centered storm. So when you have your pumps, you've got to pump it out. You know, last night's storm, you got to pump it all out because the one that filled up half the deep storage last night, it may be that the next storm that comes through to this afternoon is the one that's going to be the 100-year storm that sits on this neighborhood. So you need to have your detention empty. So you'd have to have significant level of pumping in order to keep that thing emptied within 24 hours so you're ready for the next storm. Really neat idea, really, really expensive. And historically, detention was viewed as fenced-off drainage facilities. These are some of the detention ponds that I dealt with when I worked for the city. They end up as eyesores, wasted land, not very healthy. Some of the challenges are that, you know, it's location. Where your best tracts of land are generally not where you need the detention to be. This was actually our project back in Arlington Heights, the only place because of the historic neighborhood. Nobody wanted us to remove any historic homes, so we put detention under the street. We had money to rebuild the street, so we just went ahead and tore it all out, put the detention in, and rebuilt the whole thing. But underground detention can be prohibitively expensive. City did this one, and we learned enough lessons to say they would probably never do that again. It's just not going to be cost effective. Another thing, when you start doing buyouts, just of properties that are flooded, if you leave empty lots behind, the planners call this neighborhood integrity. What happens is the lots become an eyesore. It discourages investment, encourages crime. It reduces property values now, and you really lose your neighborhood integrity. So, you know, maybe the more effective solution is if you're going to, instead of buying all 76 lots, you buy a significant chunk of lots together, and you turn it into a greenway, parkland. Perhaps you open up the stream, but you do things to make it a neighborhood amenity and not just vacant lots. Now there's ways that you can put in multi-use detention, so you can use them for aesthetics, landscaping, water quality. They can actually become neighborhood resources. Here's a couple of examples of neighborhood detention areas that the one on the left is Wells Branch in North Austin. The one on the right is LeBlanc Park in South Fort Worth. But again, detention areas that are used as soccer fields almost all the time, but when the rains come, they can fill it up and hold a significant amount of water. We actually, when I was at the city, we developed a solution in a neighborhood that had significant flooding. We talked to the school district. They had some vacant land by the Eastern Hills Elementary School, which is in the background, and Eastern Hills High School, which is just to the left of the picture. And we created a large detention basin. They still own the land. We have a maintenance, the city has a maintenance agreement with them. And for the most of the time, the water is contained either in the channel. There's also some catchment basins upstream of this, but in the major storms, the soccer field now becomes a major detention area to significantly reduce flooding downstream. This was actually so successful that we had a smaller flooding situation at one of the elementary school sites across town. This is Llewellyn Merritt. And we developed, we took their hillside and dug out a basin, put in a berm on the street side. They're now turned it into a, this is a regulation 8-year-old soccer field that's here. They also have it as a softball and kickball field, and a little paved area that the principal asked for basketball. This was actually before the basketball nets went in, but this was very well received by the school. And then this is a detention basin, also in the Arlington Heights area, a little commercial area that next to our understreet detention. We bought out, and it's a little neighborhood park. I wasn't tall enough. This artistic perspective was taken, was about 20 feet up in the air, but it does exist today. But this was a little bit better picture than what I could get from ground level. We looked at around TCU. There's a future rail station that's coming in. We've talked to some of the planners. It's real near a major flooding area. So they looked at potential. This was just a planner's concept for if you're going to have transit-oriented development in this corridor, what are some ideas that you can do that and still deal with some of the flooding issues. Some of this may or may not be very realistic, but at least we've got folks thinking about what the issues are. In some areas, they're actually daylighting streams. The picture on the left is taken probably about 100 years or so ago when they were enclosing the stream in a big culvert. Came along probably about 20 years ago and took all of that out, and they've turned it now into an amenity for the area. And it helps because the open area now has more capacity than the pipe did. It also helps reduce some of the flooding in the area. Plus it becomes an amenity. In Fort Worth, we've actually had places where the storm drain might not be fully 100 years, but we'll have an opportunity to have an overflow swale in a little parkland above it. And so we have parkland, but it can be used as an overflow swale when the pipe is overtaxed. Our conclusions are that any sustainable sink reduction, urban flooding reduction program must manage flooding in place. The detention and storage must account for timing as well as hydrograph peaks, but detention is really only acceptable as a widespread strategy if it is also a useful space for the public. In areas that are redeveloping, you know, everybody wants to build on vacant land, so you've got to make it very useful as parkland and not just detention before you get neighborhood buy-in. Now, I want to conclude today with a slightly different paradigm that helps us get to where we can find some solutions to urban flooding. This paradigm, and I'm going to credit this idea to Brenda Gasparich. She developed this for us based on Michael Lewis's book Moneyball, dealing with the 2002 Oakland A baseball team. They had about a third of the payroll that the New York Yankees did. You know, that's all they, you know, based on their fan support, based on their revenue, that's all they could really afford for payroll. And so how do you compete with another team that has, you know, can have 3 times your payroll potential? Well, if you're familiar with either the book or the movie, you have to challenge the conventional wisdom, and ultimately the numbers do not lie. So let's look what the book was talking about. Baseball teams have traditionally relied upon scouts to assess players based on observations, biases, and prejudices. There were a lot of bad investments. Hello, A-Rod. Challenged by sabermetrics, a term developed by Bill James, to look at other statistical measures. For example, the on-base percentage statistic may be a lot more important than true batting average. And in some cases, you can see the true value in players that will be bargains. Of course, if everybody else is using the same statistical measurements, then the bargains may be driven up in price. But back in 2002, the A's were faced with losing their 3 best players to free agency. They couldn't afford them to replace them with all-star players. So they signed 3 players whose on-base percentage equaled to Damon and Giambi. And actually using this particular program, they won the division in 2002. I remember the Rangers losing to them that year. And they even had a 20-game win streak during that period. What does all this have to do with flood mitigation? Well, most folks in stormwater management, you're the Oakland A's, you're not the Yankees. There's never enough funding. Your fans, the citizens, have high expectations, but you've got to compete with much higher profile funding expenditures. Traffic, roadways, police, schools, they're a lot higher profile and get a whole lot more money than drainage improvements do. So let's take this sabermetric approach to floodplain mitigation. And we'll go back to the Arlington Heights neighborhood. We have a 90-year old storm drain system. It's under capacity, mid-block SUPs, no flow escape path, frequent flooding. We've looked at all of this. And 92 homes are damaged during the 100-year flood event. We've already looked at, the conventional wisdom says we've got to provide a 100-year capacity. We look at a 24-hour rainfall event. We minimize disruption to the neighborhood. All of these things, our conventional wisdom says that we're just not going to be affordable. So what we've got to do is get beyond simply more effective solutions, and we've got to look at other issues like acceptability and affordability. It's more than just a technical challenge for us to find these solutions. And in most situations, we must find a bit of compromise in all 3 elements. So let's look at some examples, some potential solutions. First of all, the do-nothing solution is one that studies have done for decades because it's the most affordable solution. If you can't do anything else, that's at least doing nothing is affordable. Traditional solutions typically are very effective, but they're neither affordable, and in many cases they're not acceptable to the neighborhood. Tunneling, very acceptable to the neighborhood, can be very effective, absolutely not affordable. Everybody talks about green infrastructure. Green infrastructure is really cool. Everybody wanted to do that in Arlington Heights. Very acceptable, but very affordable, but in these older neighborhoods, not really effective. I think we figured out that we need at least 100 rain barrels on every lot upstream throughout the whole watershed in order to provide effective reduction in flow. And you just can't fill up 100 rain barrels with roof runoff. Buyouts may be the most affordable and effective place, but if you have a historic neighborhood, not very acceptable. Certainly not in this Arlington Heights neighborhood. In fact, they said, let's buy out the whole upstream neighborhood instead. That was the one that was acceptable to them. But obviously that's not realistic either. So what then do we find that fits in the middle? and I'm going to give credit to Burton Johnson for this idea. This is thinking about a rain gauge. Most of these urban drainage systems are small enough that they're really a 1 hour storm is all you have to look at. You look at our rain gauge, you can see the different levels of flow in a 1 hour storm, up to 3.8 inches of rain in a 1 hour storm in the 100-year, and showing the number of properties that are damaged. Our system now really only holds an inch an hour, originally held only an inch an hour. We start looking at damages and we see that, with 92 homes damaged, a 100-year storm causes $5 million of damage. Now, this was several years ago. The economics are, based on idealistic curves. But what if we look at the annual probability, so that because there's only a 1% chance, the expected annual damages of a 100-year storm are really only $50,000 per year. You do a little bit of funky economics. You remember some of this from industrial engineering class. The area under the curve equals to expected annual damages, which was $2.6 million, using the net present value and an I of 7% and 50-year cash flow. The net present value of flooding ended up being $36.5 million for this storm level. But if you really start looking at the Moneyball approach, you say, where's all the damages? The damages are really occurring in the 2-inch storm or less. So all we have to do is, if we can raise the capacity of our system, not up to 100-year, not even up to 5-year, but just from 1 inch an hour up to 2 inches an hour, we can actually reduce all the area of pink is the area of reduced damage, and the white is the only damage remaining. That net present value of damage is $7.5 million remaining in white, which means if we can just get from 1 to 2 inches an hour, we've got $29 million of benefit. So, in summary, basically, you want to challenge the conventional wisdom. You've got to rethink your level of service. We're managing flood risk, risk damage, property damage. We're not looking at public safety. We've got to rethink our hydrology to what's practical. The technology can assist us in developing this information in a larger area. We're using hydrodynamic modeling instead of sabermetrics. And we've got to develop a smart metric that's based not on some idealized situation, but on real economics. And so you can compete with the Yankees by optimizing performance and finding value. And with that, Mike, I'm going to open it up to questions. I think we have a few minutes left.
Steve, this is Bob Stevens. There's a question for
Bob.
you. Thank you so much. And if anybody else has a question, go to the Q&A and type it in, please. We've got one question, Stephen. How reliable is the 100-year event system?
How reliable? Well, there's always, first of all, there's no ever 100-year storm that really flows. You're always dealing with the fact that when the 100-year storm actually comes, there's going to be inlets that get plugged because of debris. There's going to be trees that come down and block creeks and things like that. So the 100-year storm is really but you never really get anything that's exactly a 100-year storm. It might be 100 years in one neighborhood, and the next neighborhood over is 25 years, and the next neighborhood over didn't get a drop of rain at all. So it's the whole concept of a 100-year storm is you got to have enough capacity so that you can handle, at least most events that come up, even if it's only a theoretical storm, even if it's only theoretical capacity, nevertheless, you're going to ultimately at least have more capacity available to deal with the storms that you do get.
All right, and I've got another question. What suggestion do you have for developing countries with regards to flooding?
To developing countries?
Yes. What
well, again, it's what you would do, what we would lay out with new development. You try and put policies in place so that as cities grow, the creeks are left alone. Green space is allowed to happen. You make room for flooding with valley storage. You basically set aside land from the beginning. I will say that Fort Worth went through phenomenal growth from about 1999 to about, probably up until COVID hit, but very extensive growth in certain parts of town because of the park policies that we had, because of the amount of time it took to get Clomer approved. Folks just kind of left the floodplain alone and left green space, and we ended up with a lot of green space in our new neighborhoods that ended up actually, even with some of the mistakes that were made, we still ended up with enough green space in our floodplain areas that we've got plenty of valley storage, and there's plenty of extra room in the system, so to speak, for things that don't quite function right. But the problem with developing countries is that the population, the growth is outpacing the ability of governments to keep up with it, and that's always a challenge. Somebody built something before the regulations went in place. That's what we're dealing with from what happened 100 years ago here.
And one more quick question as we're running out of time. How does the construction of roads change the flow of water in stream channels and floodplains?
If you construct, obviously hillsides, we have many cases where the amount of water coming out of a subdivision came across as sheet flow. And I remember looking at one case several years ago where the water was maybe 2 or 3 inches deep, maybe over about a 400 or 500 foot area as it came across the road. When the neighborhood came in, all the roads came in, all the storm drains came in, and it concentrated it. So even though they put in detention, what they did was they took what was maybe 1 to 2 inches of water going across the road over several hundred feet, and they basically put it all in one pipe under the road and caused a lot of immediate local damage. So one of the things you've got to look at is it's not just the total quantity of water, but it's how you're directing it and how you're concentrating it. And you're taking overland flow and you're turning it into a channelized flow that ultimately it's really, really hard to dissipate it back. We've tried big riprap fans and things like that work on a temporary basis, but ultimately, once you concentrate a flow, it's really, really hard to go back and spread it out.
Well, thank you, Stephen, so very much. Number of favorable comments, and one actually sent some clapping through the chat box.